everyone. How you doing? You're all right? Okay, so give me just a second. Okay, so we are going to play around with the problem. Well, you guys are going to play around with the problem with molality. So for C here, we have what is the molality of a 10% solution of aqueous NaCl? Now, when I say 10% here, I'm referring to the mass percent, okay? So you're given the mass percent, and I want you to figure out molality. So it's kind of going to be a two-stepper. You've got to do something with the mass percent, and then you've got to put it into the molality. Remember, molality little m, sort of cursive en, equals moles of the solvent, rather the solute, over kilograms of solvent. So you need both of these. So I'll give you all 5 minutes to play around with that. Okay, so with this one, we've got a mass percent. So if I say something is 10% mass, okay, so if it's 10% is equal to the mass percent, that's the same thing as saying 10 grams of the solute, in this case, which is NaCl, for every 100 grams of the solution. Are you all good with that? 10 grams for 100 grams would give you 10%. So if I know, hold on one second here. Come on, pen. So if I know that I have a total of 100 grams of solution and 10 grams of it are NaCl, well then I know that the other 90 grams are going to be water. I can actually go in reverse and break this up. So I've got, this is going to equal 10 grams of NaCl. And this over here will then be 90 grams of water. Right, the 10 plus the 90 gives me 100, and there's 10 grams of NaCl. So now I've got a gram amount of my solute, and I have a gram amount of my solvent. Well, I need kilograms of solvent and moles of solute. Can I get those from these two things here? Yeah, pretty easily. So if I know that I have 10 grams of NaCl, it doesn't have a zero, just one. I'll just make that a G. 10 grams of NaCl. If I want to convert that into moles, for every 1 mole of NaCl, I end up with a total of, what is it, 58.4, something like that. Yeah, 58.4 grams of the NaCl. The grams of NaCl will cancel, and we know that we have 0.171 moles of NaCl. Now, for every 0.171 moles of NaCl, I need to figure out how many kilograms of water are in it. So if we have 90 grams, we can just do a quick conversion into kilograms. Come on. I don't know why this pen is not working for me here. Oh, sorry, guys. Okay, so if we have 90 grams of H2O, H2O is the solvent, right? So 90 grams of the H2O. Well, in order to convert that into kilograms, we're gonna take this and move it over 1, 2, 3 spots. Okay, so 0.090 kilograms. Well, we can plug this information in here. If we have 0.171 moles for every 0.090 kilograms, that will end up giving us our little cursive M, or our little molality. So 0.171 divided by our 0.090. We end up with a value of 1.9. Sorry, this got a little messy here. 1.9 little cursive M. right, so let's do another one. We've got this one here. It says a solution is made by dissolving 4.35 grams of glucose. Here's the formula in 25.0 milliliters of water. And it says calculate the molality of the glucose in the solution. Now, let's assume for water here that the density is 1 gram per milliliter, okay? So you should be able to do a quick conversion from milliliters into grams. I'll give you all a couple minutes for that one. Okay, so looking at this one, so molality, which we're going to see quite a bit in this colligative properties section. So we want to be able to calculate it. So we've got our cursive little m, and it equals moles of the solute over kilograms of our solution. So we're not given moles of solute, we're given grams of solute, but that really easily we can convert 4.35 grams of the glucose or the C6H12O6. We're going to divide it by its molar mass. So 1 mole of this thing is going to be equal to roughly 180 or 180.2 grams. So this will give us a total mole value of our glucose of 0.0241 moles. Okay. We have our volume of our solvent, which is 25.0 milliliters of H2O, which is the same thing as 25 grams of H2O, because our density for water at 25 degrees, just know that that's a 1-to-1 or 1 gram per milliliter. We don't want our solvent in grams though, we want it in kilograms. So we need to move our decimal over 3, or we can shift this to 0.025 kilograms of the H2O, of the H2O or the solvent. So now it's just as simple as plugging this into our molarity our molality equation, which we put our moles on top, our this isn't working today, 0.0241 moles. Over that, we'll put our 0.025 kilograms. Work this out into our calculator. You should end up with a equal to 0.966 M value. And we have 3 sig figs everywhere, so honoring 3 sig figs. Any questions on that? If you know the equation, it's not too tricky.
Can it be 967?
If you had a rounding situation, yeah, that would be close enough. I wouldn't give you like a multiple choice where A is 0.966 and B is 0.967. Okay, we're not going to stress about that too much. Okay. So the next thing that we want to talk about are these things called colligative properties. And these are properties of solutions that depend on the number of solute particles. So if I have a solution that has, let's say it only has 1 mole of NaCl dissolved in it versus another solution that has 2 moles of NaCl. Well, the solution with 2 moles of NaCl are going to have more particles in it. So these colligative properties are going to get stronger. And these colligative properties will change the solvent. So let's say our solvent is water. Water is going to have a certain vapor pressure, a certain boiling and melting point, and a certain osmotic pressure. If I add salt to it, these things will shift or change because these particles have an effect on the properties of the solution. So looking at the different colligative properties, we're going to be looking at vapor pressure, specifically a lowering of our vapor pressure. We have this thing called boiling point elevation, so an increase in our boiling point, a melting point depression, and then a shift in our osmotic pressure. Sometimes this melting point depression is also called freezing point depression, because melting and freezing are one and the same. Melting and freezing point depression. Melting and freezing are happening at the same temperature, right? They're just either one is absorbing energy and one is losing energy. Now, an interesting thing about these colligative properties is that the changes in our colligative properties depend only on the number of the solute particles present, not on their identity. So it doesn't matter that one has Na in it and one has K in it and one has this. It doesn't matter what the actual thing is, it's how many particles are you getting in the solution. So there's this von Hoff factor, which is an I factor. It's a little italicized I. And this is used as an estimate to figure out how many particles are present in solution. Is it the exact amount? No, but it's close enough and it gives us a relative idea between different solutions. So remember when we talked about like non-electrolyte solutions and strong electrolyte solutions and weak electrolyte solutions? That comes back into play when looking at I, because what do those electrolyte solutions tell us? Well, if we're a non-electrolyte solution, we're not going to break apart. So this first one here, this is a molecular formula. It's not going to break apart into anything simpler. So we're going to say that this is a non-electrolyte solution. So if you have a molecule, the molecule itself won't break down. So we're only going to get a 1-to-1 ratio here. So if this is a non-electrolyte, so our I value for this is going to just be equal to 1. I get 1 molecule. Or I get 1 particle for every 1 molecule. Now that changes when we work with something like NaCl. NaCl is a strong electrolyte solution. So its I value in this case, well, for every one of these formula units, how many particles do I get in solution? I get 2, right? I get a sodium and I get a chlorine. So our I value here is 2, or it's going to be kind of twice as effective at its colligative properties as that original thing. Equal to 2. Okay. I want you to try and figure out C and D as far as what its I factor would be. How many particles do you think that you'll get for each of those? It should only take you, a minute or so. Okay, so both of these are strong electrolyte solutions. So if that's the case, this thing here will break apart. Remember, anytime you have a polyatomic ion, the polyatomic ion is going to stay as a packet. So I get an SO4, and then I'm going to get 2 Ks for a total of 3. Hold on 1 second, sorry. Just 1 minute. Sorry about that. So the next one here, we've got a Ionic material, this is a strong electrolyte, and we have 3 of these ammoniums and 1 of these phosphates. So a total of 4 little packets. Now, what if this was a weak electrolyte solution? Well, you couldn't really tell me your I factor. Okay, so really you're only going to have either a non-electrolyte or a strong electrolyte. Weak is, it's going to be somewhere between like a full breakdown and a partial breakdown. So just go with knowing either the non-electrolyte or the strong. So as these numbers increase, as you get kind of more bang for your buck in each one of these formula units, these properties will also increase. How do we know that the glucose is non-electrolyte? So we know that this is a non-electrolyte solution because it's a molecular solution. So good question, this is molecular. So molecular meaning that it's all nonmetals. Those are all going to be covalently bonded. That thing won't break apart in solution. Versus, what do you notice about all these? These are all ionics. It's a metal combined with a nonmetal, and they're dissolvable in water. Does that make sense? Hopefully that does. Throw it in the chat there. Cool, great. So if I was to ask you, hey, what is going to affect the solution the most, you would go with D. D is going to have the strongest effect. If you had, let's say we had a mole of each of these, this would have the most bang for its buck. So the first colligative property we'll look at is vapor pressure. The vapor pressure of a solution is going to be lower than that of the pure solvent. So if I have water versus water with salt, the water with salt is going to have a lower vapor pressure. Now, what is this vapor pressure? Well, vapor pressure is the pressure exerted by a liquid on the air above it. So if you have a cup of water, that water is exerting a small amount of push or pressure on the atmosphere above it. If I happen to have salt dissolved in that water, it will kind of pull the water down or weigh the water down. So the water doesn't exert the same amount of pressure. It will be lower. So we can actually calculate this, and let's write this somewhere. Write it a little bit farther down here. That the more solute particles, the lower the vapor pressure. Okay, so if we increase our solute particles, or if we're increasing our I, we are going to decrease our vapor pressure. More dissolved particles, less push. So we can actually calculate that using this Raoult's law, which is the PA, or the pressure of the solution, is equal to what's known as our XA. This is our mole fraction of our compound A, but it's talking about the solvent. So that's a thing that's a little bit different than what we've seen. So XA here is going to be the moles of the solvent divided by the total moles. We're so used to having that numerator be moles or grams or whatever of solute, but in this case, we're looking at solvent. So we want to know how much solvent is there over the total moles. And then P naught is the normal vapor pressure of whatever A is at the temperature. So you take your mole pressure or your mole fraction and you multiply it by your original pressure. So like, for instance, water will have a certain pressure at a certain temperature. If it's got some sort of dissolved solute in it, we would look at its mole solvent fraction and multiply it by that. Because this is a fractional value, this is fractional, our PA, our pressure with the salt, will always be lower than our original pressure. So let's look at an example of this here. It says calculate the vapor pressure of water above a solution prepared by adding 22.5 grams of lactose, and this is the formula for lactose, to 200 grams of water at 338 Kelvin. And it says the vapor pressure of water at this temperature is 187.5 torr. So the equation is pretty simple. It's just going to have two variables, really. And the hardest thing here is just figuring out our mole fraction. So let's write out our equation. We know where we're going and where we're headed. So we've got P A, or our pressure with this dissolved material in it, is going to be our XA. This is our mole fraction, times our original pressure without the material in it at a given temperature. So right here, this is the torr value. Okay, so all we need to do is we need to figure out this XA value. And so what does XA equal? XA equals our moles of the solvent, which is a little tricky, over total moles. So we've got some information about our solute and our solvent. All of those values are in grams, so we need to convert into moles. The first thing here, I know that I have 22.5 grams of lactose, which is C12H22O11. Doesn't do me much good when I'm looking at a mole fraction to be in grams. So let's get this out of grams and we'll put it in moles. For every 1 mole of our lactose, we have a molar mass of, it's pretty heavy, it's 342.34. 342.34 grams. Okay, so running that through our calculator, we find out that the total number of moles of lactose is 0.0657 moles of the C12H22O11. We also know our value of water. We have 200 grams of H2O. Again, that doesn't really do us a whole lot in grams, so let's get it into moles. So 1 mole of H2O is equivalent to 18.02 grams of H2O. And 2 hydrogens and an oxygen. Those will cancel and we can get our moles of water. In this case, most of it's water, 11.098 moles of H2O. So if we want to use this equation, we just got to make sure our values are in moles. So let's find this mole fraction, or our XA value. It's moles of solvent divided by the total moles. So our solvent is the bigger value here. It's 11.098 moles. My total moles, well, I've got to figure that out. I have to add these two together. I need to take my 11.098 and add it to my, I'm going to do that right here, 11.098 plus the 0.0657. Make sure you add those two together before you divide it out. Your total should be 11.1647. Just double check I didn't get the actual. 11.098 divided by the 11.16. Okay, and we get a mole fraction that's almost, it's almost 100%, right? It's 0.994. Okay, it's almost 1. So we take that and we multiply it by our pressure that was given to us at that temperature. So our new pressure of our solution will equal that mole ratio 0.994 times this 187.5 torr. Now in this value, this is a unitless value, right? Because it was moles per mole. So the moles canceled. So the unit we should be left with is a unit of torr, which we want for pressure. Multiply that by the 187.5. And we get 186.4. 186.4. And the unit on that is torr. So it's pretty close to our original, but it's just slightly less, right? So if it was just water, we would have a push of 187.5 up. Adding a little bit of lactose, we have 186.4. I want you to solve this exact same problem, but I'm going to shift it. Instead of saying that we have 200, or rather 22.5 grams of lactose, let's really add it up. Let's say we add 78.3 grams of lactose, C12H22O11. Okay, so we'll kind of call this like a part B. So we're gonna up our lactose. Our guess should be that this torr should go down even farther. I'll give y'all 2-3 minutes for that. And keep everything else the same. So keep the grams of water the same and keep the torr at that temperature. We'll keep the temperature the same. Okay, so if we change our lactose amount and we increase our lactose value, that's going to increase the number of moles that we have of lactose, right? So instead of 22.5, we've got 78.3 grams of lactose. We divide that by our molar mass of lactose and we get 0.22, we'll go with 229 moles of our lactose, our C12H22O11. So the water is the same, right? We didn't increase the amount of water. So I can actually keep my numerator value the same. But what's going to change is that my denominator value is going to get bigger because my mole value for my lactose is bigger. So here we're going to take that 11.098 moles and we're going to add it to 0.229 moles. We end up with 11.327. So we'll take our 11.098 and divide it by the 11.327. And we get still a large fraction, but now we're getting 0.979. So we'll go with 9780, round it. Take that value and multiply it by 187.5, and we get 100. Let's put this in 0.980. I get 183.7 torr. Okay, so last time where it was 186, now we're at 183. So you can see as you increase this lactose value, right, this number is going to continue to drop because our fraction is going to continue to drop. At a certain point, though, there's only so much lactose you can pack into your solution. So let's move on to the next property, which is boiling point elevation and freezing point depression. So whenever it's cold and icy and snowy, what do you throw on your icy steps? Salt. Okay, this is why we put salt on our icy stairs. It's also outside of not just flavoring, but we put salt in our water when we boil pasta. So people think, oh, well, it makes it boil faster. It doesn't make it boil faster. It boils at the same rate, but it makes it boil at a higher temperature. So the food will cook faster. So we can draw over here. I need a new Wacom pad. I got an iPad, but I don't know how to hook it up as a drawing tablet yet for my computer. So I'm still using this old school Wacom pad. So boiling point is going to increase. And I'm going to say that it's 100 degrees for H2O. And then freezing point is going to do the opposite. So it's going to decrease when it's traditionally 100 degrees and 100 degrees Celsius for H2O. Let me put a little C there. So traditionally, and most of the time, everyone, we're going to be talking about solutions in water. We're not going to be talking about them dissolved in other things. So 100 degrees Celsius is when water boils, 0 degrees Celsius for when water freezes. But if I start packing ions in there or particles in there, the boiling point's going to increase and the freezing point's going to decrease. So in a situation where we have water on the stove, if I throw salt in it, depending on how much salt I throw in there, it's going to take the boiling point from 100 degrees Celsius to maybe 110 degrees Celsius. In that case, the water can actually get hotter than 100 degrees. It can get to 110 and the food and the pasta can cook faster. And you also flavor your pasta. The opposite is true with freezing point. If I have ice outside, it freezes at 0 degrees Celsius, right? But if I throw some salt on there, well, now I've created a solution where the freezing point drops. So instead of freezing at 0 degrees Celsius, let's say it freezes at -5 degrees Celsius. And let's say it's only -1 degree Celsius. So now the freezing point is lower than the temperature outside. The material will melt, the water will melt. These values are the changes in freezing point and boiling point are directly proportional to the molality. Okay, remember molality is our moles of solute over kilograms of solvent. So that's going to come back into play here. And these equations, this one is for the change in temperature of the boiling point. This is for the change in temperature of your freezing. They're very, very similar to each other. They both have molality and they both have your I value. The difference there is that there's a constant. So this KB is the molal boiling point elevation constant. And this is specifically a property of the solvent. So this would be given to you or it would be in an appendix somewhere. So water will always have a constant KB value. It'll always have a constant KF value as well. As far as M, little m, that's our molality. So that's our moles of solute over our kilograms of solvent. And then we have our I value, which is our von Hoff factor, which is dependent on how many particles we have, right? So something that breaks down and we get a lot of particles, we're going to see that change increase. So let's play around. Oh, one thing to note, the change in TB. So whatever value this equation pops out, that's not the new temperature, it's the change in temperature. So you would want to take your change in boiling temperature and add it to the normal boiling of the solvent. So if this thing, we plug this, our information into this equation and we get a change in boiling of 3 degrees Celsius, our new boiling point isn't 3 degrees Celsius, it would be 100 plus the 3 degrees Celsius. The same thing is true for our TF, our change in temperature for freezing, but this you're going to want to subtract from the freezing. So if our TF for this value ends up being, let's say also 3 degrees Celsius, we wouldn't be at 3 degrees Celsius for a freezing point. We would take 0 degrees Celsius and subtract it to give us a -3 degrees Celsius. So if we look at a problem, we can look at automotive antifreeze. Consists of ethylene glycol. So it's the C2H6O2. It's non-volatile. It's also a non-electrolyte, which means that you just get one of these for every molecule. We're not breaking apart. This says calculate the boiling point and freezing point if we have a 25% mass percent solution of ethylene glycol in water, and it gives us our KB value and our KF value. So we're going to have some sort of change in our boiling and our freezing point. So let's just write out our equations for each of those. So the change, the delta B, change in boiling is going to equal our KB times our molality times our I. Sorry, let me put a temperature. Delta T, our change in temperature of freezing, will be similar to this, but it's going to be our KF times our molality times our I. And you know what? Pause, I skipped over something here. I want to go back up here. So let's do this before we do this. Okay, so which aqueous solution will have the lowest freezing point? So let's say all of these are dissolved in, let's just say they're in water. Okay. So the change in temperature of freezing is going to equal our Kf factor times our molality times our I value. So in order to figure that out, I mean, we can sort of just conceptually look at, well, these has, this has a lot of particles. This doesn't have a whole lot of particles. That might come into play, but this has a higher molality. So we really want to just go ahead and calculate it out. We don't need to take into account the Kf, because if we're dissolving in the same solution for all of these, that will be the same for all. So we really only need to look at our molality times our I value, and whichever one has a higher molality times I is going to have the bigger change or the lowest freezing point. So for this one here, I've got CaCl2 and its molality is 0.050. So I'll plug that in as 0.050 molality. And I'm going to multiply it by my I factor. So my I factor here is 3, right? A calcium and 2 chlorines, or 3 particles. So we'll multiply by 3, and I get a value of 0.15. And this is sort of unitless, so don't stress too much about that. This here, it gives me my molality is equal to 0.15 M. And then my I factor for this one is 2, right? 1 sodium and 1 chlorine. So I don't have quite as many particles here, but I do have a higher molality than what I had before. So when I plug this in, I get 0.30. All right, what's going on with my hydrochloric acid? My molality is 0.10. And my I factor would be, well, in this case, it would be 2, right? 1 hydrogen and 1 chlorine, so 2. So this works out to 0.20. Again, these are sort of unitless. We're just comparing the numbers. I could plug in the Kf for every single one of them, but I don't have to. This big clunker right here is a molecular non-electrolyte solution. We have a nonmetal mixed with all nonmetals. So in this case, I'll have the 0.050, but I'm only going to multiply it by 1 because I just get one of these. So my ending number here is 0.050. Same thing with this one here. This is also an non-electrolyte solution. So my molality value of 0.20 is just going to be multiplied by a factor of 1, just 1 molecule. So 0.20. So when looking at these, if I was to determine what would have the lowest freezing point would be derived by the biggest change in my TF. Well, that biggest number is going to come from whichever one of these is biggest. And in this case, it would be this guy right here. This is the perfect combination of a high molality and a relatively high particle factor. Yes, this first one had a higher I factor, but it had a much lower molality. If I was to say which one would have the least effect on freezing point, it would be, let's see, 0.2, 0.05. I would say this one here. This would be our lowest, D. We're only getting 0.05. So back to this problem. We want to figure out what the boiling point and freezing point of something that has a 25.0 mass percent solution. So KB I have, it's given, and KF I also have. KB and KF I have. In my I also have, because if it's a non-electrolyte solution, I should just be 1. So I equals 1. KB given, KF given. So really, I just need to figure out my molality of this. So remember, molality equals moles of solute over kilograms of solution. Do I have either of those? Or not, I'm sorry, not kilograms of solution, kilograms of solvent. And do I have either of those? Not really. What I have is this thing here. I know that I have a 25 mass percent. So this problem is going to be very similar to what we did with that very initial problem where we had the 10%. If I have something that's 25% mass percent, I can assume I've got 25%. I can assume that it's 25.0 grams of the solute, which in this case is my ethylene glycol. So our C2H6O2. And if it's 25%, it's over 100 grams of the total solution. Now, I don't want my denominator here, kilograms of solvent. That's not talking about solution. It's talking about the whole solvent, or just the solvent rather. So I need to break this up. Oh, come on. Sorry, this pen is. So we're going to break it up into its solute and its solvent. So we already know what the solvent, or rather the solute is. We've got 25.0 grams of the C2H6O2. So if the total is 100 and 25 is being occupied by the solute, then the solvent, which is water, has to be the remaining 75 grams of H2O. This is getting closer to what we need here, but what do we have to do with this? This needs to go to moles, and this thing just simply needs to go to kilograms. So let's convert our 25 grams. 25.0 grams of ethylene glycol, C2H6O2. If we divide it by its molar mass, it'll get us into moles. The weight of this thing is 62.1 grams. So our mole value of C2H6O2 is 0.403. If I have 75 grams of water, I can really easily convert that into kilograms, 0.075 kilograms of H2O. Right, I just moved the decimal over 1, 2, 3, and filled the 0 in. So my molality for this thing, which are these two numbers divided by each other, is 5.37 little m. Make a little space here, get rid of this. So now we can go back to these two and we can figure out our change in boiling and our change in freezing. For our change in temperature and boiling, we take our KB, which is this 0.51. We multiply it by our molality, which is 5.37. And then we just multiply it by our I factor, which is super simple for this one, it's 1. All right, and I get a change in temperature of 2.74 degrees Celsius. Now we can't really stop there because it's not asking us for the change in temperature. It's saying, hey, what is the actual new boiling point? So we need to take that value and we have to just add it to the 270, or I'm sorry, add it to the 100 degrees Celsius. So our new boiling temperature, or our new boiling point, is going to be 102.74 degrees C. Now, the freezing isn't going to be much different. The only thing that shifts is our KF value. So we have 1.86 here. So it has a little bit more of an effect on the freezing than it does on the boiling. We have the same molality. It's still 5.37. And we still have the same I value, which is 1. So in this case, we have a value of 9.99 degrees Celsius. And again, it's not enough to just write that, because the problem isn't saying what's the change, it's saying what is the new freezing. So in order to create the new freezing, we need to take what our original freezing is and we subtract it. So remember, add it in boiling, subtract it in freezing. So here we've got to take our 0 degrees C. Because if we're boiling, we're at 0 degrees Celsius, and we're going to subtract the 9.99 degrees Celsius, which will give us a total of negative 9.99 degree C. So our boiling point went up to 102.74. Our freezing went down to negative 9.99 degrees C. Any questions on that, on using the equation, the K, the TB, the delta TB, and our KBs and our KFs? Remembering these will be given to you. This is really just as simple as counting up the particles. The hardest thing with these problems is going to be right here, calculating the molality. So if you feel comfortable with calculating molality, you've got most of the work done for the problem. All right, we're going to pause there. We'll get into osmotic pressure next week. And then, like, literally, this is the last of the semester, is this osmotic pressure stuff. So then after that, we'll have time for review. All right, so if you can sometime this weekend, go over your notes and stuff, see where you feel strong, where you feel weak. And then I can give you guys some example problems. We can practice the stuff. Your test for all of this stuff won't be this Sunday, it'll be next Sunday. So let me know if you have any questions. You can stay around. If you have any questions on your grade, where you're sitting, anything like that, let me know. Otherwise, is it Thursday? I guess enjoy your weekend, right? Enjoy the weekend, and I'll see you all on Tuesday.
Thank you.
Thank you.